Our next speaker is Alex Adam from the University of Montreal. He's a PhD student studying with Laurence Barrel-Levasseur, studying recurrent inference machines, score-based modeling, and gravitational lensing. And please correct any French names I've mispronounced. Thank you.
Okay. Is that good? Yeah. Okay. So in this talk, I'd like to tell you a bit of an adventure that I had in the past couple of years studying high-dimensional Bayesian inference. So high-dimensional here in this context will mean typically images. Images are made up of tons of pixels, tens of thousands, and each of these pixels we want to infer their values. But the discussion will apply in general to high-dimensional inverse problems, so you can think of spectras or videos is going to be the same. Now, I don't study these types of problems for fun. What interests me is actually learning something about dark matter using gravitational lensing as a tool. So here is a famous example of a gravitational lens where you see the distorted image of a blue galaxy here that forms an Einstein ring. And of course, it's the galaxy here that you see in the middle, which is actually in front of the blue galaxies in our line of sight. That's distorting the image of the blue galaxy. Okay, and by studying these distortion, essentially what we can do is learn something about the gravitational field of the object in the foreground, right? Or equivalently about the mass. And if we can learn something about the mass, then we can infer something about dark matter, right? But that's a hard inverse problem because you want to go from this image data back to other images. So an undistorted image of the background source, and maybe also learn something about the dark matter subhalos that are predicted to be permeating the whole universe, right? Not necessarily massive enough to produce galaxies that we see, but that should have a gravitational field which will distort slightly these light rays. And if we can do this inference precisely enough, then we can maybe distinguish between different scenarios of dark matter, right? Where here you would see cold dark matter and where warm dark matter models would have less substructure. Okay. But this is hard, and so typically what we do is we make the problem a bit simpler, so just to start. And so we assume, for example, that we know the gravitational field, and what that does is it turns the inverse problem into something that's linear. I'll tell you more about this later. And just using neural networks, we can start to improve upon what traditional method would do, but it's still not quite enough to do the science we want to do, right? Like there's still residual, which means that our inference is not precise enough yet to get at the level where we can start to distinguish these small distortion. And we also need uncertainties because actually we're not interested that much in this source that we're inferring here. I want to marginalize over these parameters to get at the dark matter signal, right? So this is what initially motivated me to study diffusion models, right? So at this point, people typically know a lot more these days about diffusion models, so I'll just say a few things, which is that what you want to do is start from a distribution. So in this example, here is galaxy images, and perturb these images until you get only pure noise. And what you do when you do this is you learn a score, okay? And then to sample, you start from noise, and then you get at other modes of your target distribution. So that's just sampling from the prior. In the foundation model era, we would say that training this score is sort of like a pre-training phase. This is typically very well understood. So here's a package that I wrote to do this. It's very easy to do. What's more interesting is like the second part where you actually sample. And here, basically what we did by adding noise, we've specified a set of distributions. So not just the target distribution, which I've labeled here, px naught, but a set of distribution going from a distribution that's hard to sample from, galaxy images, to something that's much easier, just a Gaussian. And then by adding an infinite amount of these, we actually set a partial differential equation which set the evolution of this distribution. And equivalently, this sets a description, like a prescription to actually sample from this thing, which is this SD. Okay, but the crucial part is that you need a score to actually go from the high temperature distribution to your target. Now, just modifying this SD here allows us to do inference. Okay, so the only thing I would like to say here about this slide is that you don't need to retrain the neural network or condition it on the observation. What you want to do is just add a term to the sampling procedure, which you can craft yourself with the knowledge you have about the measurement, the noise, basically everything you know about the physics of observing. All right, so this likelihood typically is a Gaussian likelihood that we just had here. I'll say more about this later, but because there are approximations involved. But for a simpler problem like linear inverse problem, we get a good handle on this term that we can add. And so what this does is by adding the term, we're modifying the dynamics to solve a problem, okay, without retraining the neural network. And so we did this a couple of years ago for the source reconstruction problem in gravitational lensing, and we got a good result. And what's interesting as well is that, if we take a source which is not from the training set of the prior, we're still able to get posterior samples, that solve the problem accurately and get uncertainties that sort of make sense, right? So if we have constraining observation, we get very tight posterior, and if we have less constraining observation, we get something more closer to the prior, right? Actually, I like very much this paper, which kind of took this idea, roughly same setup, but applied it to the Event Horizon Telescope. So they started from a prior train on people spaces, and then you had the likelihood of the Event Horizon Telescope, and then if you only if the likelihood is not so constraining, you kind of get these spaces, but you still see a bit the contrast from the shadow. And as you add more constraints, you get closer to what's been reported in the past. So that's pretty interesting. And so we were inspired by this. So we tackled ALMA observations of protoplanetary disks. So here, just a little background in interferometry. Basically, what you observe are the Fourier modes of the sky, but you don't observe all of them. So there's an inverse problem in recovering an image from this. But you get a lot of Fourier components, so the likelihood should be constraining. And then what we do is, well, these are tiny objects on the sky, so you need to define a prior, but we don't have images of these protoplanetary disks from optical telescopes, so we just take galaxies, and then we hope for the best. And actually what happens is that we do better, much better than algorithms that have been used for decades in the field, just from this misspecified prior. Right? So much sharper images, and on top we get uncertainties. And the reason we want uncertainties is because typically you don't just want a pretty image, right? Where you want your science is going to be downstream of these things. So you want to propagate uncertainties down to what you care about. And just as an example, like not only do we get sharp images, we can start to ask questions like, oh, are these features real, or are they meaningful, or are they exoplanets forming in these protoplanetary disks? You can imagine that if we trusted those uncertainties, and that requires calibration, which I'm not going to show in this talk, then you can start to say, well, okay, this feature that I've observed here happens with an 80% probabilities in my posterior sample, so that's my confidence. And you can do this for different features. So that's an example of sort of downstream science. I'll just say a word here, which is, so far I've talked about the priors, but if your noise is not Gaussian, right, you can also use a diffusion model to learn a score over your likelihood, right, but just by training it with example of noise and plug it in the same framework. And if you combine the two, you can sort of start to do inferences from data that is much more raw. That's typically, if you were to feed this to a neural network, it would just crash and burn, right? But here, we just apply this Bayesian framework where, we encode everything we know about the physics of observing, and then we start to do much, much, much better than, so here, this is an example of PSF deconvolution, which just means that we try to recover a clean image, an idealized image from the blurry, noisy image that are observed by the telescope. And this is real data, right? This is real HST data. And then, we infer stuff about like the structure of these galaxies that is like hidden in the noise. It's pretty interesting. And here we took just to make sure we weren't like hallucinating these things, we compare with like a James Webb observation of the same field, and we found that the structure we're inferring was actually consistent with the James Webb observation. Okay, so all of these examples, and you could build like diffusion models for similar problems, which are linear inverse problem. What that means is that your observation is linearly related to your parameters of interest, which are like x here, by a matrix with constant values, okay? And so like all the problems that I've talked about share the structure. And any problem which has this general structure can be solved by these methods, roughly speaking, okay? So you can use these diffusion models to learn priors, likelihood for linear inverse problems, and then solve them in one shot like this from a pre-trained sort of like base model that was completely agnostic to the task. Now, in general, though, the issue is that this likelihood term, if you actually do your statistics properly, it's actually supposed to be intractable. Okay, what this integral here is at the bottom, what it says, as I solve my diffusion, which typically like, you're gonna discretize the SDE, so you're gonna have maybe like 1,000 steps or something, where you take a step toward the gradient and then you add noise, and you do this like 1,000 times until you solve the problem. What this means is that for every single one of these steps, you're actually supposed to run a full diffusion, right? That's the expectation here. For every xt, you're supposed to run a full expectation over what the prior things could happen, as you diffuse down to 0 temperature. Well, that's like diffusion squared. So, you're not going to do this. But for linear inverse problem, there's like a cottage industry of like approximation that exists here. I'm just listing a few. There's way more. And actually, it's been known for a long time that, here it's like a Kalman particle filter. Like it's been known since the 80s that you could do this. We just discovered this with the diffusion model. But the sad thing is that as soon as it's nonlinear, there's actually nothing you can do. At least there's nothing better than just trying to estimate this intractable integral. And that's annoying, because the problem that I want to solve is one of these. So, okay. Right, if I want to learn about this, I have to somehow solve something that's nonlinear, right? So if I was smart, I would just give up. But I'm in Montreal, and there's these guys that tell me about GFlowNet, and they're like, oh, Okay, so what is a GFlowNet? So actually, yesterday we've learned about like RL. Okay, a GFlowNet is like basically RL with just like a new twist. Okay, it's the same thing. Actually, they just fight with like RL people over definition all the time. It's quite fun to read these like review NeurIPS and okay. So what's the setup? Okay, so previously I said like if you train a diffusion model, okay, you have sample from the base distribution, and you just add noise, so you just create all of these intermediate until you get the Gaussian. It's very easy, right? So you start from the base distribution and you add noise. If you want to solve an inverse problem, well, you don't have samples from the posterior. That's your goal, getting these samples, right? So you start from the distribution up top, and now if you have a linear inverse problem, then you can roughly guess what those distribution would be, down, up, that solve the problem. But for the nonlinear inverse problem, you don't have an unbiased way to do this. Okay, and you don't have samples, so you cannot just create them out of thin air. So how do you think about this problem? The way GFlowNet thinks about this problem, so let's simplify it, okay? So let's think about like a very simple situation where I have like a single state, and then I think about transitions to, like in this case, only 2 states, okay? And I'm gonna think about just particles flowing down pipes, okay? And then this is the example that's typically given, but like you can think about, you cannot lose particles the same way that like if you have like liquid flowing down pipes, you should not expect the water particle to just tunnel out of the pipes, right? So whatever happens at the end, you should still have like if you sum all the final states, you should have 100% probability, okay? And that's a sampler. That's what a sampler should do, okay? And so what the RL problem is that you're only given probabilities over the final state, and you have to guess, for whatever structure of your problem is, what the transition probabilities should be, such that you kind of like respect this basic property of like not losing particles. And also respect the probabilities that are given by the reward function, okay? So when you build a sampler, there are basic things that you want to respect, okay? One of them is detailed balance, right? So if you think about a node, you want the inflow to be equal to the outflow. That's kind of basic, and we call it detailed balance, okay? So the trick is to turn this into a loss, right? So that's what GFlowNet do. They say, okay, we want this, so we're going to turn it into a loss. Now, detailed balance is more like it's a local thing about a single state, but like if you want to make it a global property, you can think about, so this is trajectory balance, which basically just sum these detailed balance term, okay? And you can see that there's like some cute math that happened where there's cancellations, and then you get your reward function there, which is the likelihood, right, the log likelihood. And then these P here, these transition probabilities, is technically what you have to learn. Okay, and the way you learn, and what's important about this loss is that, like, unlike, the way typical RL problems are framed, typically they're framed with a KL divergence, and they'll put the expectation over what the model, the policy generates. Okay, but that has problem, right? You get mode collapse if you do this for basic reasons. Here is kind of like a global property of the sampler. You could generate these trajectories out of any policy, including the model, but like anything else. And that's a good thing. That's a good thing because, in principle, if I generate these trajectories in a smart way, maybe I can avoid these mode collapse actually. So that's the hope, okay, of GFlowNet, is to say, can we train these policy or fine-tune policies of these diffusion models such that I can somehow find a sampler from my nonlinear inverse problem, that solves the posterior. Okay, and can I train it in a way that makes sense? So there was a couple of, so I think that work is like 1 or 2 years ago now. But so this is updated. So trajectory balance is kind of like completely agnostic. So you have to train this from scratch. It's really hard. Here, what we're doing, I came to these guys and I said, I have my prior already. Like, I don't have to start my thing from scratch. Like, I can just have my base model and just update it. All right, so like the relative trajectory balance just says, okay, so instead of learning the policy from scratch, we're gonna start from the prior, which is a bit better at least. Or prior doesn't have to be a prior. Like, you could condition the diffusion models, and so it would be an approximation for the posterior. And then the hope is that fine-tuning the model with this loss, you would obtain like a valid sampler. Okay? So some result. So for example, here they would fine-tune like commercial diffusion models on prompt. And I think the loss was something like RLHF, which is reinforcement learning with human feedback. So there's some argument about whether humans are nonlinear functions, but whatever. So if you train it with like normal RL, you would get this. You would get something a bit better with RTB. And the green rabbit and cats and dogs. So this is nice. And then, then we applied it to gravitational lensing, and then we start to, for the source reconstruction problem, which is linear, but we start to get like good things and even improvement upon the, yeah, I'm done. So, okay. So this is kind of like an adventure towards figuring out something about, oh no, I thought I was 10 minutes off, but okay. So we want to learn something about dark matter. This is my conclusion slide. So all of these examples that I've shown are basically kind of like steps inching toward trying to solve this nonlinear inverse problem to ultimately try to learn, about dark matter. Obviously, like, it's way harder than what I thought it would be initially, but ultimately it's interesting. I get to work at the frontier of these machine learning thing, and the GFlowNet has been quite an experience. And so I would like to leave you with this slide. Thank you.
Thank you, Alex. Questions?
So in the diffusion model, the second, your alternative approach to the diffusion model for the linear problem, I am not an astrophysicist. Can you just explain where the nonlinearity comes in?
Okay. So for a given mass distribution like this, basically what you're doing is you're moving around the points of light, so you're distorting the image, right? So the nonlinearity comes in the fact that the response is strongly dependent on the value of the mass. So for example, if the value of the mass is low, right, the response is very small. But as you get to like higher concentration of mass, you start to get like very strong warping. Like you can create like small, tiny rings inside the. Of general relativity. Of general relativity, right? So we.
Just a general relativity thing. And how did you get away with it before? Right, sorry, too many questions.
No, it's a good question. So the way this is done typically is that, so instead of trying to solve it for this map, you would like guess a profile that's much lower dimensional, right? And then that gives you a handle on the problem a little bit. But that also biases you, and it lacks the expressivity to figure out, but in most cases, it lacks the expressivity to figure out these dark matter subhalos. Yeah.
I have a question. Oh, sorry. Let me interject with a question of my own, if that's okay, just briefly. Hi. So in the graphics community, there's this whole cottage industry of speeding up diffusion models using teacher-student networks and so forth. I just wondered, do you find those valuable, or is it not is that a valuable direction for you?
So for the linear inverse problem, so it's not needed, but for the second part, for the nonlinear, like, so then we get into computational problems that are pretty significant in terms of if the sampling policy is very expensive, then it gets really hard to fine-tune them. So in that case, yes, every trick that we can find to speed up the sampling procedure is helpful in helping for the fine-tuning. Yeah.
Thanks. And there's a question over there.
Hey, Alex. Following up on this idea, or on the question of nonlinearity, right? If you use the nonlinear solver to identify a simplifier profile, which is the traditional way you just mentioned, can you locally linearize?
Okay. Yes. Yes, you can do this, and in fact, this has been mostly our approach. So I didn't show results, but like we have work in the pipeline where we do this, right? Because once we realize, okay, so it's not linear, so we're not going to be able to do the full thing, we broke it up like this. And the reason it's been taking us so long to just get this out is because ultimately we'd like to trust the uncertainties in the calibration. Like, we don't just want to say, here's a map and do something with it. We want to say, like, we're confident that this is this, and then this is a temperature of dark matter. So it's been 2 years trying to get a handle on these uncertainties, basically. Yeah.
Okay, so yeah, I'm here.
Yeah.
Right. So actually, okay. So since you tried Gaussian filters and because of the nonlinearity, so have you checked state space representation selection active? So it's a way of literally it's like different way of transformers. So it's making Kalman filter in a way of learnable, and you can add activation function to make it nonlinearity. So I believe it might be helpful. I'm wondering if you checked it. It's actually new.
We can talk after. I haven't tried this, so I'm not familiar. Yeah.
Yeah, sure. Okay, thank you.
Other questions?
It's nice to see the uncertainty on the pixel level. Can you say a bit about the trustworthiness of that uncertainty?
Yeah, I didn't put any plot, but yes. So we have. I don't know if you're familiar with TARPS. That's a paper that came out maybe like 2 or 3 years ago. But it allows you to build these coverage for high-dimensional things. So now it's very expensive to do it because typically, sampling from these images. Order of magnitude might take like a minute on a GPU, and you have to solve hundreds of inverse problems. So it gets expensive, but we did this for a linear inverse problem, trying to see if some of our approximation were giving correct coverage, and we don't get perfect coverage still. So we get something close, especially for very informative likelihoods. So for the protoplanetary disk example, maybe not so far from a good coverage, but there's no approximation yet that gets the perfect coverage, even for these linear problems. So I think if we wanted to make to do very strong science, even for the linear inverse problem, we might need something like the fine tuning that I mentioned, or some version of this.
And on the sorry to push you on this, but on the nonlinear, maybe in some toy models, you say where you reduce dimensionality or so. Can you say something?
Well, if the dimensionality can be reduced, then that obviously gets easier, right? The thing that I'm talking about is high dimension where we're fully facing the intractability of the problem. That makes sense. You don't necessarily need you don't necessarily need diffusion for the lower, if that makes sense. The diffusion is this trick because the modes are highly separated because you're in a high dimensional space. Right, so every image is far from each other. If you just do a Euclidean distance, so that's why we do this annealing procedure. But then the problem is that in the prescription for how we do the annealing for the high dimensional that's what's hard. If you have a lower dimensional thing, there's many MCMC sampler that are gonna solve this without needing the. If that makes sense.
Yes, but then you could see, obviously, how well you're doing by using the other method.
Oh, yeah. No, we haven't done that. All right, we have toy problem, but we've mainly been focused on the high-dimensional part. Yeah.
Thanks for the nice talk. I was wondering, have you applied this to some of the systems where the Hubble constant measurement is debated? There is this mass sheet degeneracy.
For the Hubble constant, there's a fierce debate, and I try to stay as far as possible from. But there's a team for gravitational lensing, so they don't need high dimensional stuff. They do pretty well. The thing that was blocking the H0 measurement from gravitational lensing was mostly getting a handle on the kinematic, trying to get independent measurement of the mass of the galaxy, basically. Yeah. So no, I've mainly been focused on this this problem here. Yeah.
But yeah, they also have like some analytic models for the lenses versus you have like something more.
So those are results that are kind of come in. Like I didn't put anything here, but like in the coming months, yeah. Like we have reanalysis of for example, slack lenses. Yeah. So just for the source reconstruction with the linear stuff, that's already pretty interesting, and you get really, really pretty images of these background galaxies, which already is interesting for many science, but yeah.
Okay, let's thank Alex again.